What if I told you there's a way, at least on paper, to jump across the galaxy in seconds? Not with warp drives, not with hyperspace, but through a shortcut in the very fabric of spacetime. We've seen it in science fiction, from Interstellar to Doctor Strange. Wormholes are everywhere. They're those cosmic tunnels that supposedly let you travel from one point in the universe to another instantly. But here's the real question. Do wormholes actually exist? Could they be more than just a plot device? And if so, could we ever use them? In this video, we're diving deep into the real science of wormholes. We're exploring how physics allows for them, at least mathematically, why they might be unstable, and what it would actually take to travel through one without, being ripped into quantum spaghetti. A wormhole is basically a special kind of solution to Einstein's general relativity equations. Imagine it as a tunnel connecting 2 points in space or even time, but this tunnel is way shorter than the normal distance between those points. So, it's like a cosmic shortcut. Sounds like sci-fi, right? Well, wormholes do exist as legit mathematical possibilities in physics, but as far as we know, nobody has ever actually found one, and we definitely don't know how to keep one stable in the real universe. The first wormhole idea came from Einstein himself, along with Nathan Rosen back in 1935. That's why these are sometimes called Einstein-Rosen bridges. They started by looking at the math behind black holes, those crazy dense points with an event horizon beyond which nothing escapes. Then, they extended that math to include the theoretical opposite of black holes, white holes. Now, white holes are a bit wild. Instead of sucking stuff in like black holes, they're thought to spew everything out, and nothing can enter them. Einstein and Rosen imagined that every black hole could be paired with a white hole somewhere else in the universe, and a wormhole could be the tunnel linking these two. Sounds cool, but here's the problem. White holes, if they exist, would be extremely unstable. If you tried to toss something toward a white hole's event horizon, that thing would never actually get in. Instead, energy in the system would just keep piling up until, boom, the white hole would explode. Plus, even if white holes were real, the only way to get through such a wormhole would be to cross the event horizon of a black hole side. But once you cross that point, you're trapped forever, so objects could enter the wormhole, but never come out the other side. And if that wasn't enough, wormholes made from black and white holes would be fragile. Even just a single particle of light passing through could destabilize the tunnel and cause it to collapse. Fast forward to the 1970s, and physicists started figuring out how to make a wormhole stable enough to actually pass through, a traversable wormhole. The key? Move the entrance away from the black hole's event horizon and find a way to keep the tunnel open so that matter traveling through wouldn't cause it to collapse immediately. This is where exotic matter enters the picture. Exotic matter is a hypothetical form of matter that has negative mass. Something that sounds weird, and it is. We haven't ever found this stuff, and it seems to break some of the basic rules of physics, like conservation of momentum. Imagine placing a negative mass object next to a normal mass. They'd start accelerating forever without any energy input. Wild, right? If a stable wormhole like this did exist, it would look pretty strange. The entrance would appear as a sphere, kind of like looking at a planet's surface. Peek inside, and you'd see light coming from the other end of the tunnel. The wormhole's length could vary, and as you traveled through it, you'd see distorted, shifting views of the parts of the universe you were coming from and heading toward. But wormholes don't just bend space, they might bend time too. Thanks to Einstein's theory of special relativity, we know that clocks moving near the speed of light take slower than stationary ones. So, if you could move one end of a wormhole at near light speed, time at that end would lag behind the other. Bringing the two ends close again will create a time difference, meaning one entrance could lead you into the past. Basically, you could walk through one end of the wormhole and pop out in your own past. This sounds like science fiction, but it's a genuine theoretical possibility based on what we know about physics. Still, nobody has a clue how to build a wormhole or if it's even physically possible. One promising candidate to replace exotic matter is negative energy, which shows up in quantum physics. The vacuum of space isn't empty. It's filled with fluctuating quantum fields, which carry intrinsic energy. Sometimes, in a local region, these energies can be lower than the surrounding space, effectively creating a patch of negative energy. This negative energy is real and measurable in the lab as the Casimir effect, where two metal plates placed extremely close together experience an attractive force due to this weird quantum energy difference. But whether this negative energy could stabilize a wormhole is a huge open question. The negative energy we see in experiments is only relative compared to its surroundings, not absolutely negative, which might be what a wormhole would need. Some physicists think that tiny wormholes could naturally pop in and out of existence at microscopic scales within the so-called quantum foam, the chaotic, fluctuating fabric of spacetime itself. But even if that's true, it's unclear how these tiny wormholes could grow big enough for humans or spaceships to travel through, or be stable enough to stay open. If you're diving into the world of wormholes, exotic matter is the mysterious ingredient everyone keeps talking about. But what is it exactly, and why do we need it to keep wormholes open? First off, exotic matter isn't just any weird stuff. In physics, when we say exotic matter, we mean matter that has negative energy density, or negative mass. Yeah, that sounds crazy, but stick with me. Normal matter, the kind we're made of, plants, stars, you name it, has positive mass. That's why gravity pulls us together. But exotic matter flips the script. It would have negative mass, meaning it would repel normal matter and gravity would behave differently around it. Remember how we talked about the Schwarzschild wormhole? It's a neat mathematical idea, but totally useless as a shortcut because it collapses the second you try to go through it. The problem is that gravity always wants to crush that tunnel shut. The intense pull from the mass surrounding the wormhole's throat squeezes it tighter and tighter, eventually snapping it closed. Here's where exotic matter comes into play. If you could stuff the wormhole's throat with exotic matter, this stuff with negative energy and negative mass, it would push back against gravity's crushing force. Instead of collapsing, the exotic matter could hold the wormhole open, creating a stable tunnel you could theoretically travel through. Think of it like this. Regular matter pulls everything in, like a vacuum cleaner. Exotic matter would do the opposite. It would act like an anti-vacuum cleaner, pushing outward and keeping the wormhole from collapsing. However, exotic matter isn't something we've ever seen or isolated in the real world. It's totally hypothetical. Physicists have never confirmed any real, stable material that behaves this way on a large scale. If it did exist, it would break a bunch of the rules we take for granted, like the conservation of momentum, basically how things move and react to forces. To make it even weirder, exotic matter might allow some wild phenomena like faster-than-light travel or even time machines, because it messes with the fabric of space-time so drastically. That said, we do have glimpses of negative energy effects in the quantum world. One famous example is the Casimir effect, when two super-close metal plates attract each other due to fluctuations in the quantum vacuum between them, creating a tiny region of negative energy. But this is microscopic, and not something you can just scale up to keep a giant wormhole open. Scientists also talk about quantum fields, and the idea that space-time at tiny scales is a bubbling, fluctuating foam where weird stuff like microscopic wormholes might pop in and out of existence. Maybe exotic matter, or negative energy, happens there on a tiny level. But how to control or grow it? That's a whole other challenge. So exotic matter is basically the theoretical magic ingredient that will make wormholes stable and reversible. Without it, wormholes collapse or are one-way traps. But since we don't have any proof it exists, wormholes remain firmly in the realm of theory and science fiction. According to Einstein's general relativity, wormholes, or warp holes, come from the way space and time curve under extreme gravity. But that's really where the similarities between wormholes and black holes stop. Black holes pull everything in and trap it forever. Wormholes, on the other hand, are like cosmic tunnels that could let matter pass through, connecting two far-apart spots in the universe, or maybe even linking different parallel universes. But simply, black holes act like giant cosmic vacuum cleaners that suck in matter and energy with no way out. Wormholes are more like bridges, potential shortcuts through space and time. The key to keeping these tunnels open, as I said before, is something called exotic matter, which creates a kind of gravitational push that stops the tunnel from collapsing on itself. That's the main thing that sets wormholes apart from black holes. So, while both black holes and wormholes involve intense gravity and mess with space and time, they're totally different in how they're built and what they do. Black holes are well-studied and real astrophysical objects, but wormholes are still purely theoretical. We haven't found any evidence they actually exist yet. Nope, a wormhole can't destroy a black hole. Black holes are incredibly stable astrophysical beasts, and as far as we know, there's no natural process that can take one down. Now, if a black hole and a wormhole somehow cross paths, the black hole could swallow the wormhole if the wormhole got too close, inside the black hole's event horizon. But if the wormhole is way bigger and stable enough, meaning it has enough exotic matter to keep itself from collapsing, then a smaller black hole might actually pass through one end of the wormhole and come out the other side. That said, if the black hole's mass is strong enough to seriously warp the space-time around the wormhole, or suck up some of its exotic matter, the wormhole would probably collapse as a result. According to research from 2020, astronomers think they might be able to spot black holes falling into wormholes by looking for weird fluctuations in gravitational waves. If wormholes exist at all, that is. So, can wormholes just pop up naturally in the universe, or are they something only an advanced civilization could build? That's a big question scientists have been digging into for decades. First off, wormholes aren't just sci-fi inventions. They come straight from Einstein's general relativity equations. The math allows for these bizarre tunnels connecting different points in space and time. But the big mystery is whether these tunnels actually form on their own, or if you'd need some super advanced tech to make one. One popular idea is that wormholes might naturally exist on a tiny, microscopic scale. This comes from the weird, jittery nature of space-time itself, known as quantum foam. At unimaginably small scales, far smaller than atoms, space-time isn't smooth and calm, but frothy and turbulent. It's like looking at the surface of the ocean up close and seeing constant bubbling and popping. In this quantum foam, tiny wormholes might be forming and disappearing in a blink. If these microscopic wormholes do exist, they'd be way too small for anything meaningful to pass through, definitely not a spaceship or even a particle. The problem is, no one really knows how to scale up these tiny tunnels into something stable and large enough for travel. The forces that keep quantum foam popping constantly would also tear apart any bigger wormhole before it could last. On the flip side, there's the idea that wormholes could be artificial structures, created by an advanced civilization with technology far beyond ours. Building a wormhole would require not just manipulating space-time, but also exotic matter. If any civilization could figure out how to gather or generate enough exotic matter and control space-time precisely, they might engineer stable, traversable wormholes. These could be used as shortcuts for interstellar travel, allowing instant travel across vast cosmic distances. It sounds wild, but given the universe's age and the possible existence of civilizations millions or billions of years ahead of us, it's a scenario some physicists take seriously. There's also speculation that natural wormholes might have formed during the very early universe, right after the Big Bang, when conditions were extreme and spacetime was highly curved. During that chaotic time, some patches of spacetime might have pinched off and created wormhole-like structures. If so, some of these primordial wormholes could still exist, hidden somewhere in the cosmos. But the problem with these early universe wormholes is the same as with tiny quantum ones. Without exotic matter, they would collapse almost instantly. So even if they formed naturally, their lifespans might be too short to be useful or even detectable today. At the moment, there's no observable evidence of either natural or artificial wormholes. They remain hypothetical constructs supported by equations, but not yet confirmed by real data. Future advances in gravitational wave detection, high-energy astrophysics, or quantum gravity might one day provide clues. Now let's talk about something that's fascinated humans for ages: time travel. Books, movies, and countless sci-fi shows have explored the idea of jumping back or forward in time. But what if I told you that wormholes, those hypothetical tunnels through space-time, could actually offer a real way to travel through time, not just space? Here's the science behind it. Wormholes connect 2 points in space-time, potentially even different moments in time. But how? This all boils down to Einstein's special theory of relativity, which introduced us to the concept of time dilation. Time dilation means that time doesn't tick at the same rate everywhere. The faster you move or the stronger the gravity you're under, the slower your clock runs compared to someone else's. For example, astronauts on the International Space Station age just a tiny bit slower than people on Earth because they're moving fast relative to us and experience slightly weaker gravity. Now, imagine you have a wormhole with 2 ends. Both ends are synchronized. Clocks at both mouths tick at the same rate. But here's the trick. If you take one end of the wormhole and accelerate it to nearly the speed of light, the clock at that end will slow down compared to the stationary end. This is classic time dilation. When you bring the 2 ends back together, one end will have aged less than the other. In other words, the 2 wormhole mouths are no longer synchronized in time, they're out of sync. That means the wormhole could connect not only 2 different places in space, but also 2 different times. What does that look like in practice? If you enter the fast-moving mouth, you might step out of the stationary mouth at an earlier point in time, effectively traveling into the past. Conversely, traveling in the other direction could send you forward in time. This creates a fascinating loophole in physics. Wormholes might allow time travel, at least in theory. But time travel via wormholes opens a whole can of paradoxes and headaches. One of the most famous time travel puzzles is the grandfather paradox. Imagine you jump back in time and accidentally prevent your grandfather from meeting your grandmother. That means one of your parents would never be born, so you wouldn't exist either. But if you didn't exist, how could you have traveled back to stop your grandparents from meeting? It's a logical contradiction, basically a time loop that breaks itself. These kinds of paradoxes are why many physicists are skeptical that time travel to the past can actually happen. They mess with cause and effect in ways that seem impossible. Enter Stephen Hawking and his chronology protection conjecture. Hawking proposed that nature might have built-in safety checks to prevent time paradoxes from occurring in reality. Essentially, the laws of physics would somehow stop wormholes from becoming time machines that let you mess with the past. How would this work? The details are still debated, but the idea is that when you try to create conditions for time travel, like moving a wormhole mouth at near light speeds or manipulating exotic matter, quantum effects might kick in. These effects could cause the wormhole to become unstable or collapse before any paradoxical trip can happen. In other words, while the math might say time travel is possible, the universe would stop it from actually happening by protecting the timeline. Hence, chronology protection. What's wild is that the idea is consistent with what we see. No verified time travelers have popped up, and we don't observe the universe breaking causality, cause and effect. However, chronology protection remains a hypothesis. We don't have experimental proof yet. Wormholes themselves haven't been detected, and exotic matter, the key to keeping wormholes open, is still theoretical. So time travel, paradoxes, and chronology protection all sit in the space between mind-blowing theory and the limits of our current understanding. Wormholes remain one of the most fascinating yet unresolved ideas in physics. Despite decades of study, they are still largely theoretical. The main challenge is stabilizing a wormhole, which seems to require exotic matter, something with negative mass or energy. While quantum effects like the Casimir effect hint at negative energy, we don't know if it's enough or suitable to keep a wormhole open on a scale large enough for travel. Another big question is whether wormholes form naturally or if they're purely mathematical solutions. Some theories suggest tiny wormholes might exist in the quantum foam, the complex, fluctuating structure of spacetime at extremely small scales. However, how or if these could grow into stable, traversable tunnels remains unknown. On the observational side, tools like gravitational wave detectors might someday identify signals linked to wormholes or their interactions with black holes, but so far, no clear evidence has appeared. Looking ahead, progress depends on advances in quantum gravity and a better understanding of spacetime and exotic matter. These fields might reveal whether wormholes can exist physically or remain just theoretical constructs. In short, wormholes are far from confirmed, but continue to push physics forward by challenging what we know about the universe. The search for answers may take many years, but the effort itself drives new insights into the nature of space, time, and reality.